Assalamualaikum. Today I will present my part on simulating power system response of IEEE 50 machine 145 bus test system model for power system stability analysis. So this is my group member Muhammad Farizul, Hafizuddin, myself Nizam, Kamaruzaman and Nurhayatul Fikri. Okay, for the introduction, power system is defined as one of more generating unit, loads and power transmission line, including the associated equipment connected to it. So power system stability is the ability of electric power system for a given initial operating condition to regain state of operating equilibrium after being subjected to a disturbance. It can be divided into two: steady state stability and transient stability. Okay, for the background, in order to remain synchronized after being subjected to disturbance, the ability of rotary angle stability needed in interconnected synchronous machine in power system. Okay, it depends on the ability to restore the equilibrium between the electromagnetic torque and mechanical torque of each synchronous generator. Okay, the instability occurs when some of the generator angles swing higher than the other that can cause the loss synchronization in the system between the generator. Okay, so for the objective we got three. The first one, we have to work in group to solving the problem by using our knowledge in power system analysis course, and we also learned the way to modeling the design of power system using MATLAB software. So the last one is to understand the suitable protection schemes to ensure power system delivery and sustainability. For the scope, the test model we use in this project consists of 5 generators and 145 bus bar, and we use MATLAB to stimulate and analyze the response of the generator. The last one, the stimulation model, is based on the transient stability of the system. Okay, for the literature review, there are three. Okay, the first one, if the acceleration is higher than the area of deceleration, the generator will accelerate before it slows down completely and will eventually become stable. The second one, if the deceleration area is larger than the acceleration area, the machine will decelerate completely before it accelerates again. And if the rotor inertia will force the subsequent acceleration and deceleration until it attains the steady state. If the two areas are equal, they will become boundary of the stability.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Khairul Zaman bin Muhammad Jamri. Okay, this my part is methodology. Okay, this is the flowchart we use in this project. So from the flowchart, we can know that the methodology used for this project. Okay, for the first, we will run the software for this project. Okay, for the software that we use is MATLAB software. Okay, after that, from the MATLAB software, we will insert the data into the MATLAB software. So the data that we use is data 50M and SCMU source code. Okay, the next slide, I will show you about the example of the data 50M and source code. Okay, this data 50M, okay, we can see that from the bottom of this slide, the example of the data 50M. Okay, the next is about the SCMU source code. Okay, this is the SCMU source code we use for this project. This is the kind of the example we use for this project. Okay, after we insert data, we will run the software. So from that, we will find the time for clear fault and clear remote. For this task, we have the 4 condition case, which is stable case, critically stable case, critically unstable case, and unstable case. So from this case, we must find the real suitable time for this case to get the exact response result. For our result, we will compare the power system response with power system stabilizer PSS and automatic voltage regulator AVR, and also without power system stabilizer PSS and automatic voltage regulator AVR. Okay, after we get the data from the clear fault and clear mode, okay, from that we will get a tree graph. So from that, the graph is about the voltage of magnitude measured at the fault bus, rotor angle response for all generator during fault, and also the generator speed response for all generator during fault. Okay, for this assignment, we use 50 generators and 145 bus bar. Okay, from the graph that we got it, we will analyze the graph successfully.
Hi, my name is Muhammad Huriyatul Fikri bin Muhammad Syukur, CE 150206. For this result, we will see in the four cases. First is stable case, critical unstable case, and unstable case. For stable case, the fault clearance time is set to 0.01 second. The start time with the same value there is 1.08 second. You can see here, the start at 1.08 and the clear fault at bus 6. For voltage of both magnitude measured at the fault bus, with PSS and AVR, voltage stable at around 7 start. For without PSS and AVR, the stabilized voltage start around 8. The rotor angle response for all generator during fault, for with PSS and AVR, the highest rotor angle response is about 98 degree, which is the radian is 1.0104. For without PSS and AVR condition, the highest rotor angle response is about 170 degree, which is the radian is 2.04. The generator speed response for all generator during fault. For with PSS and AVR condition, the highest generator speed response are about 11.7 multiplied by 10 the power of negative 3 per unit RPM. For without PSS and AVR, the highest generator speed response are about 0.012 per unit RPM. For critical stable case, we will see in two conditions also with PSS and AVR, and another is without PSS and AVR. We use critically unstable case where the fault clearing time is set to 0.01 second after the fault occurs, delay in about 0.03 seconds. For with PSS and VR, the time start response is 1.13 seconds. We can see here a clear bar at bus 6 here. And without PSS and AVR, the time start response is 1.10 seconds. So also the clear bar at the bus 6. For voltage critical stable, for which PSS and AVR, voltage stabilized after 7 seconds from the start of simulation time. For without PSS and AVR, voltage start stabilized after 8 seconds from the start of simulation time. Rotor angle response. For with PSS and AVR condition, the highest rotor angle response is about 80 degrees, which is the radian is 1.39626. For without PSS and AVR condition, the highest rotor angle response is about 95 degree, which is the radian is 1.65806. The generator speed response. For with PSS and AVR condition, the highest generator speed response is at 0.017 RPM. For without PSS and AVR condition, the highest generator speed response is at 0.013 RPM.
Okay, Assalamualaikum. My name is Muhammad Farizul Mahiruddin. This is my part, critical unstable case. For this critical unstable case, we have two conditions, is with PSS and AVR and without PSS and AVR. In this critical unstable case, we use with the fault is clearing time is set at 0.01 second after the fault occurrence, and the delay is about 0.03 second. Okay. Slide is this is the with the PSS and AVR, the time start response in 1.14 second, and without PSS and AVR, The time start response in 1.11 second. Okay. Next slide is voltage critical unstable, and with the PSS and ABR, this is the graph that we get, and the voltage critical unstable after 3 seconds, and without PSS and ABR, the voltage critical unstable after 4 seconds. Okay. Next is roto angle response. This is with PSS and ABR, the graph, and the rotor angle response is about 3.3 times 10 to the power of 4, which is the radian of 575.95865 radians. And without PSS and ABR, the graph, and the rotor angle response is about 3 times 10 to the power of 4 or 5 to 3.59878 radian. The next is the generator speed response. This is with PSS and AVR. The graph, and the RPM is 0.27 per unit RPM, and without PSS and AVR, and the RPM is 0.26 per unit RPM. Okay. For unstable case, the fault clearing time is set to 0.01 second. The started time with same value there is 1.17 second. Next, the time of the system response. This is the data. And the voltage of both magnitude measured at the faulted bus. This is with PSS and AVR. The graph that we get. The voltage unstable after 3 seconds. And without the PSS and AVR, the voltage unstable after 2.5 seconds. Okay, the rotor angle response for all generator during fault. With PSS and AVR, 3.8 times 10 to the power of 4, which is the 663.2251 radian. And without PSS and AVR, 2.6 times 10 to the power of 4 or 453.78591 radian. Okay, next slide. The generator speed response for all generator during fault. This is without PSS and AVR. The generator speed response are about 0.27 per unit RPM. Without PSS and AVR, the generator speed response is about 0.32 per unit RPM.
Hi. For the conclusion is, this project presents the transient stability analysis of 50 machine, 145 bus test system model for the fault occur in the bus 1 to 1 until 1 to 5, and it is considered as a disturbance. And for this project, we are present in 4 cases, which is we will see in a response in each case. First is stable case, critical stable case, critical unstable case, and unstable case. That's all from us. Thank you.